All right, welcome back to Open Analysis Live. This is part 2 of a 2-part Unpacker series that I'm doing. So if you haven't already watched part 1, go back and check it out. At the end of part 1, we were left with the first stage of the unpack binary called stage1.exe. So if we pop over to our IDA instance here, we can see we've already loaded up stage 1. That we extracted in the first part of the series. We've loaded it up, and as you can see, I've already done, because this is more of a walkthrough than a live tutorial, I've already done a bit of analysis. I've already put in some labels and put in some breakpoints, but I really hate it when people skip steps. So what I'm going to do is I'm going to just show you how I determined, how to call these, how to label these functions, because there is a lot of dynamic API resolution here where so if we look at our imports, there's only 2 imports, create process and message box. So you can see that obviously they're going to be doing a lot of dynamic importing. And then if we pop back to the view, you can see I've already sort of labeled things like terminate process or create process. So I want to show you quickly how I did that, and then we'll fast forward and assume that you did that for all of them. So what we're looking at here is after I've already labeled the functions, and you can see here's kind of a trick that, like, I think everybody knows this, but I'll just mention it anyway. One of the things I like to do is if I don't know what a function is, like here I've just called this double garbage, more garbage. What I like to do is I just like to give important functions that I'm going to be looking at. I want to just give them some sort of string name that I can remember so that I can keep it separate from functions that I haven't already looked at. So this is like sort of like more of like a malware triage thing where you don't really care too much about what's actually going on. Like you don't want to have to analyze all this crap. You just want to, sort of get to the important bits and take a look at those. So the way I do this is sort of just keep giving names to all these different functions. If they have like a call to, so here I'll just show you like the create process. If we see where that's referenced here. So you can see like create process is called in this function. So I just called the function, I just called it wrap create process. I don't really know if that's what it's doing. I'm just giving it a name so that it stands out when I'm looking at the assembly. It makes it a lot easier to read. So that's just like one of the tricks. I think everybody does this. I just wanted to mention it in case you're very new to reverse engineering. It's just a really helpful thing to do. So like I was saying before, there's no imports, and I had to go through and manually let's go to start and manually figure out what all these imports were. I could have scripted it, but and I'll actually talk about that in a minute. But what I just want to show you how to do everything very simple and manual for the tutorial, just so you know like how it's done, manually before we get into like automating this stuff. So I'm also, just before we get into that, I also want to take a look at the sample that's been uploaded to Hybrid Analysis. So not my favorite sandbox, but since malware.com is down right now, we're going to use this. And I didn't want to use like my internal sandbox because I want something that you guys can actually have access to, so you can look at the same results that I'm looking at. So if we look at this, it was actually submitted as fun, but it's the same exe. So, if you don't trust me, I can show you hashes afterwards, but it is. So if we look down here at the processes that were spawned, we can see that when it was run, it spawns explorer.exe, and we can see that actually did run. So there's like some network traffic, some interesting strings maybe that were extracted, but really all we care about though is the API calls. So we can see that there is probably going to be some process injection into explorer.exe. So if you click on the process and you click on API calls, Again, hybrid analysis is really a pig when it comes to this stuff. Like it's really not good. Cuckoo is significantly better for looking at API traces, but we make do with what we have. So what I'm going to do is I'm just going to show you at the end of this trace. So we go to the final API trace, and we can see terminate process, resume thread. And if you missed the part one of this tutorial, I just talked a little bit about process injection. So I'll just do a quick reminder here. When you're doing process injection, there's like a few different very common patterns that you'll see. Now, this sample is exciting because it doesn't follow those common templates, but it has some of the similar characteristics. So the two most common templates are to create a process suspended, then write process memory, so you write something into that process, and then resume thread. So that's number one. That's the easiest, simplest way to inject into a process. The second way is to create process suspended, map a view of that process memory into your own process, write to that view, and then resume thread. So these are like the two most common ways that you'll see process injection done. And if we look here, we can see that resume thread. We can see some map and unmap view, right? So it looks like this one is following, it looks like this malware is following the second type of injection where they're using maps. But I'll show you as we get into this that it's actually much more complicated than that. So normally, if they're using maps, one of those map views is going to contain the PE file in it. So because, again, this is going to be difficult to follow if you're not really familiar with how processes are mapped in memory. But basically, a PE file will be mapped as a bunch of different segments in memory. So if you're using process injection, you need to inject those segments into the memory of the process that you're injecting into. So you can't just like load an entire PE in. So there's really two ways if you're using like MapViewOfSection. So one is to map view of the entire PE file, and then you just load those sections in wherever they need to fit inside the entire process. This is really easy to extract the injected PE file from, because you'll have the whole map, right? So you'll have like one memory segment that has the entire PE file in it. Another much more common way is to have a map for each section in the PE file. So if there's like a text section, data section, R data, whatever, you're going to have that many maps. And so for those, it's a little bit more complicated because then you have to extract each section. So you might have to extract like 4 or 5 different sections, and you need to recombine them into the PE file. So again, if you're not super familiar with how that works, you just look up like process injection. There's a million tutorials that are way more interesting than my bald head talking. So go check those out. But basically, in this scenario, they're using a bit of that technique, but I'll show you it's definitely not what you think. So basically with that, we're going to dive in. We know that these are these API calls, like the MapViewOfSection, create section, resume thread, create process. These are all API calls that we want to hook, right? So that's kind of like we go from the sandbox to IDA. That's kind of what we want to be doing. So again, that's why I'm trying to resolve these APIs so I can find out where I want to hook. So here, what I'm going to do is I'm going to walk you through just one of the APIs that I resolved manually. So let's pick this query information process. So if we take a look at the function here, let's assume that I didn't know that it was query information process. So when I was doing this the first time, I would look at the function. There's not a lot here. I don't really want to dig into anything, but I do see at the end of it this jump EAX. So anytime you see like a control flow change to through a jump EAX or a call EAX, something like that, it's always going to be of interest to you, because that's not normally how you would change control flow, right? You're not generally going to be jumping to an address saved in a register. You see this a lot in malware, where these jumps are either going to be like, silly stuff that they're doing where they're jumping to like unpack code, or they're going to be jumping to dynamically resolved APIs. So what I'm going to do is I'm going to throw a breakpoint on here, and then I'm just going to run through. I'm going to run it in the debugger until I get to that EAX. And then at that point, I'm just going to check and see what it actually calls, right? So what EAX points to. So let's do that now. We'll just hop over here. I do have a few other breakpoints set, so I'm just going to have to jump through those. Okay, so now we get to jump EAX, right? So let's just hover over here. We can see IDE actually has labels already pre-populated. So you can see here EAX points to NT-query information process. So we can see, okay, this whole function, it looks like, since that's the last argument, right? So it looks like this whole function is just a big wrapper to dynamically call NT-query information process. So then we can just label it like this. Now, so I'll stop running now, and I'll remove that debugger breakpoint. So now what we can do is, if we go back to where this was called from and start, we can start looking at all these different functions. So if we let's say look at create heap, we can see, oh, this is actually not as good an example. It's a little bit messy. There's a lot of garbage code and junk redirects and stuff like that in here, just to make it difficult to analyze. And I kind of don't want to go into that. You can waste a lot of time trying to figure out what these functions are, when really we already know what this is doing from looking at the sandbox run, right? We already know that it's going to do a create process, and then it's going to inject something into that process using MapViewOfSection. So we've already seen that in the API trace. So there's not a lot of point in trying to figure out what all this crap does. All we really want to do is just hook those calls and call it a day, right? So so basically what we want to do is we want to roll through all of these different functions and see any functions that have this oh, here we go, here's a call EAX, right? Or any of them that have a jump EAX. Just put breakpoints there, run in the debugger, and then relabel the function with whatever API call was called out to. Now, so again, I've already done that, and to save time, I'm not going to go through it. This is actually going to be a long tutorial anyway, so I don't want to waste time doing that. But at least now you know how to do it. And one thing I would suggest is, because we know from, if we hop over to hybrid analysis here, and we look at that API trace again. So because we know that at the very last traces before that process is resumed is going to be an NT-resume thread, what I would suggest is, while you're going through and labeling the code, because you don't really know what it's doing yet, right? You're just running through it in order to label it. I would suggest putting a breakpoint on NT-resume thread, and then that way, if you ever get there, you can just stop debugging, right, and restart over again, because you never want to, you don't want to actually execute the injected process, right? So the injected process is going to be started in suspended mode anyway, and the only way that it resumes is if somebody calls resume thread on it. So all you have to do is put a breakpoint on NT-resume thread in IDA. So if we again, if we start in the debugger and we pop over here into NTDLL and we go to NT-resume thread, where are we at here? Did I miss it? There we go. So if we go to NT-resume thread and we add a breakpoint here, we know that we're never going to get messed up, right? So we know that we're always going to hit that breakpoint before the injected process resumes. So we're pretty safe to just run the debugger at will, and we're going to be pretty safe, right? So that's kind of the trick I would say to use if you if you want to start labeling the code with the debugger live. It is pretty fast. Like I mentioned before, there is a way to script this, because it's going to be a call EAX or a jump EAX. You can actually just write an IDA script to put breakpoints on all of those opcodes, and do it that way. But I don't want to, I really want to focus on like the manual portion of this analysis so that you guys get, how it's like done basically all the steps, and then you can go ahead and script it up if you want to. Okay, so if we go back here, let's jump back to start. Oh, right. Stop, please. Are we at our start function here? Yep. So as we go through and sort of read the code here, we can see there's we're going to start to see some familiar stuff. I don't really care about the create process anymore. I'll just delete that breakpoint, and I think I have a breakpoint in create process as well. Yeah, I'll just delete that. Okay, so I don't really care about create process. What I care about are those create section and map view of section, right? Because like I was saying before, that's how you get your code into another process. That's how you inject your code, or at least that's what it looks like from the API trace in the sandbox. So here you can see I've put a couple breakpoints on reprocess memory, and I will take just a minute to explain how this works. So obviously, when you first attach to a process, so then when you first create a process suspended, you don't know anything about that process. So in order to get information such as like where the image base address is, just information generally about the process, you need to get the process environment block, the PEB. And so that's what you'll usually see with process injection. You'll usually see a read process memory from the process where the PEB is, and then they'll parse the PEB manually with like pointer math, in the code. So I did put, I was actually confirming this before, but again, it's not particularly important for this tutorial. So I'm just going to remove those breakpoints. So what's going to be important to us, again, delete that breakpoint. What's going to be important to us is these create sections. So I'll add a breakpoint to create section, map view of section, create section. I'll add another breakpoint here, map view of section. Now I've already gone ahead and cheated a little bit, and I have a pointer to a data segment inside this PE file. And so like if we jump there, we can see it's actually the R data segment. And if you want to know how I did this, basically if you look at IDA at this, like, I'm not sure what this is called actually, but it's like a map of like the memory of the PE, and it's color coded. So if you're not familiar with how this works in IDA, see the little arrow that's pointing to like where you are in the code, so you can move around. Everything that's blue is like analyzed like code data, right? So it's code. Things that are, well, here actually here's the color map right here. So we have data unexplored is stuff that they haven't, that hasn't been analyzed. And you have like instruction data here, but really when we see these big blocks of like this greenish yellow color, that usually means like, and we see that there's only a tiny bit of function code here. So that usually means that this is packed, and this is the packed section in the PE. That's generally like, if you look at like packers that are just tiny stubs for the packer and then a big executable embedded in it, this is kind of the layout that you would usually see. Just a tiny bit of blue and then this big like greenish yellow blob here. So all I did was I just popped over to the beginning of the greenish yellow blob, and it's the R data section, and I just put a label here called compressed data. I just assume that it's going to be compressed data because it's, this is a packer and this is a big blob of data, and we can see that it's referenced in the code. So I put a breakpoint here. We can actually remove it now. It's not particularly interesting for this tutorial, but it is, it's something that like I would normally want to breakpoint there, and that I kind of want to watch what actually happens to that code to that data during these routines, just to see if it's actually unpacked in place. So again, this is kind of like a trick that you might get more familiar with the more packers that you look at. But in this case, it's not really super relevant to what we're doing. So we'll scroll down here. Here's another map view of section. Keep scrolling down. An unmapped view of section, I'll talk about that in a minute. A map view of section, and then resume thread. So if we look here at all of our breakpoints, it looks like we've been able to put breakpoints for all of these. For all of these API calls that we can see in the sandbox trace. So it looks like we managed to grab all of them. You can even see that they're in order in that they appear here. So it means that we got the right ones. So I did say I'm going to talk about unmapped view of section. So if you're going to map if you're going to map code from your process into another process that you're injecting into, and it already has code in that section, you're going to need to unmap that code. So a lot of the time you'll see an unmapped view section of a remote process, so the process that you're going to inject into, and then a map view of that segment into your process, so you can actually write code to it. So that's why this is important to see this unmapped view of section here. And again, like I was saying, we have it grabbed in IDA with a nice breakpoint here. So where are we? So before we can make sense out of this, we just need to go over some basics with section mapping. So in order to use like map view of section to write code from your process into another process, each section will need to have two mappings, right? One mapping into the remote process where you want to write the code, and one mapping into your own process where you're actually writing the code, right? So you're going to write it into a memory segment in your own process, which is mapped to a segment in the other process. So one section, two mappings, one remote, one local, okay? And it's kind of confusing to like keep track of this. So what I'm going to do is I'm going to just, I'm going to have a notepad here, and I'm going to just sort of set this up so I have the section handle. So I'll do like a section handle, and then I'll do a remote address, and I'll do a local address. So we can sort of keep things, clear as we go through and step through the code. The other thing I want to do is I want to talk a little bit about the actual arguments that are passed to map view of section. So let's do a map view section. So for those of you who aren't familiar with Microsoft internals, Windows internals, the ZW function is just another entry point for NT functions. So we can look at, and NT functions aren't documented by Microsoft, but ZW ones are. ZW ones are used for like kernel programming, whereas we're in user land looking at the NT interface for NTDLL. So these arguments here are going to be the same for NT map view of section, the same for ZW map view of section, or at least the same for these important ones that we're going to talk about here. So for the first argument is going to be section handle. So this is the actual handle to the section that you've created. The second one's going to be the process handle. So the handle to the process that you're going to be doing the mapping from. Now, again, if you're not familiar with Windows internals, invalid handle or like a null handle is going to be -1 or all Fs, and that means your own process, right? So if you have like a process handle that's all Fs or -1, it means, use my own process. Don't use another process. And then we have the base address, and the rest of this we'll worry about in a bit. But the first three arguments are the most important. And of course, the base address, if you're mapping from a remote process, is going to be the address in that remote process. And if you're mapping in your own process, it's going to be the address in your own process. So that's basically all there is to it. Let's pull up my notepad again here. And we'll pop over to IDA and we'll start debugging. And every time I hit create process or create section, and MapViewOfSection, I'll take a note in the notepad. Now, the goal of this is going to be at the end, if we look down, we keep on following these all the way down until resume thread. So there's going to be a final MapViewOfSection here. And what we want to do is we want to take a look at the data that's in that final MapViewOfSection and see whether that contains the unpacked PE file. So this is like a trick. Again, we're trying to do this fast because, again, trust me, there's a lot more stages here. So we're trying to do this quickly to see whether we can just extract the injected PE file, being kind of lazy with just a couple API hooks. So without further ado, let's get into it. Again, every time we have a create section, okay, so let's pop over create section and let's find out what the handle was for that. Now, I'm not particularly interested about the actual section until it's mapped. So let's pop down until we get to the first mapping here. All right, now I'm interested. So if we look here at the arguments on the stack, so the section handle is 48. It's a local process mapping, and the address here, let's copy this here. And let's take a look at the address. All right, nothing in that address. So let's jump over it. Okay, so we have mapped this address here from our own process to handle 48. So let's mark that down. So section handle is 48, and we're at local address A4000. Okay, so let's continue on now. And if you missed what I did there, all I'm doing here is I'm just looking at the value of the pointer on the stack for the base address. So that's why I opened another window here to take a look at it. So let's continue on. Here's another create section, which again, I don't really care too much about the create sections until I start mapping them. So let's get to MapViewOfSection. All right, here it looks like it's another section, handle 44, again, a local mapping. And let's step over it and see what the address was that was mapped. So here's the pointer on the stack. Copy that, and then let's go take a look at it. Go v. Okay, so we've mapped this address locally, and so that's 44, and it was local, and the local address was 8B000. So this is pretty tedious, pretty tedious work, and I do apologize. We do have to do a couple more of these, but you'll see in the end, this is definitely where it's at. So here we can see there's a remote process. So we can see the process handle is 54, so it's no longer a local process. The section is 44. And the address that we want to be mapped at, let's take a look here. All right, let's pop over this and let's take a look here. So the remote address is 9 and 4 zeros. And it's to section 44. So section 44 remote address is 9 and 4 zeros. Okay. Now I'll keep going. And I have a unmapped view of section. So I think I might have already mentioned this, but if you are going to map your code into another process, you need to unmap the code that's already there. So sometimes you'll see an unmap view of process that just simply unmaps a bunch of code that's already there, not for like a section that doesn't exist. This is just basically a way of clearing code out of the process that you're going to inject into. But it's also used to unmap views of sections that we've been using before. So what's important here is we want to check the handle and make sure that we're not unmapping a view that we've already mapped. So let's take a look here at the unmap view of section. And yeah, sure, let's just look at there should be like a ZW version of this. Just like I said, so there's the process handle and the base address. So these are like the two arguments. So let's go back and we'll take a look and see the process handle. Why are things a little messed up here? I think there's a bunch of extra stuff on the stack here that maybe gets popped off. Yeah, I think there's a bunch of stuff that gets popped off in this function. So but what we're actually looking for here is we can see that the process handle is 54, which we know is the remote process, and the base address that's being unmapped is this big sucker right here. So let's pop back over to our notepad, and I'm just going to mark down unmap in remote process. Okay. So what that's doing is that's clearing out a code segment in the remote process. So now let's go down to this last MapViewOfSection. Okay, interesting. We have it's going to be for section 48, and it's going to be in the remote process. And let's take a look here. Go to this address and take a look at it. So it's going to be at that address that we just unmapped. So let's go back and look at our notepad, and I'll explain the whole picture of what's just happened here. So keep in mind that it's remote process, this giant address that we just unmapped, and it's section 48. So let's pop back to our notepad. Section 48 here, right? And it's being mapped into this address in the remote process, and it's going to be this local address. So let's take a look here at what's, I'm sorry, I have to copy that address. Let's take a look at our code and see what's actually being mapped, right? So what's actually in our process that we're mapping into that address. Because again, that looks like an image-based address. This looks interesting to me, especially since we just unmapped it. So let's come over here and we'll go to that address and see. Oh, hey, look at that. It's a PE. So at this point, we can see, just to go back through it all, we are now mapping a PE into that process over where because it's explorer.exe, I know that that's the image-based address. So we're mapping at the image-based address. We're mapping a PE file into it. So this is kind of like I was explaining. This is very similar to that process I was talking about before, process injection, the second one where you use MapViewOfSection to inject code in. So what we can do now is we can take a copy of this code that's being injected in, unmap it, and then take a look at it in IDA and see what it does. Now, there's one other thing I want to do because this is kind of interesting, and this is where things get a little bit tricky. So I'm going to pop back to our notepad, and you can see, remember, we also have another mapped section that's mapped in at 9 4/0 hex into the remote process. And it hasn't been unmapped, right? There was no unmap call for that. And if we look here, the next function call is resume thread. So they're going to actually execute that process with that map section mapped. So I'm going to take a copy of that section too, just in case. I want a copy of that just in case it's important and, for some reason. Generally, you would unmap it if it wasn't important, and then so you can clean it up. But for some reason, they're leaving it mapped into the process when they run. And I can tell you now that this is the trick, right? This is the key trick, and why this is difficult to unpack if you're just using, if you think of it as just a normal process injection, because there's a second step here. So without spoiling the fun, let me copy those two sections out, the one that has the PE in it, and then the other mystery one that's mapped at 9 4/0, and then we'll take a look at what they are. So first thing I'm going to do, like I did in the previous tutorial, I'm just going to go over to my hex view, and I'm just going to copy the HexBytes and save as a file. So first I'm going to go to this address here with the MZ, and I'm going to copy it out. Now, one of the things you might have noticed me doing before when I copied the data out was that I didn't seem to care about copying extra bytes at the end of the PE file, and that's because it doesn't really matter. As long as you get the bytes that are used in the PE file, you can append a bunch of junk data onto the end of it. So if you accidentally copy a bunch of an extra bit of a buffer, it doesn't really matter, because when the PE is actually mapped, that data will just be ignored. So all I'm doing now is I'm just scrolling down until I see the end of the buffer, and which then I know that I can stop copying at the end of the buffer. So I'm just, oh, here we go. Looks like we hit the end pretty soon. There's a bunch of garbage here. I might have gone past it. Remember, I'm looking for that FEE unused memory segment here. It's just, I think I'm well over where I should be. One of the ways that I could have sort of done this a little bit better is I could have looked at the length of the section to be mapped, and I could have copied that out, but I didn't think about it at the time. I was too busy trying to explain everything as I go. So I'm just gonna, I'll just copy down to here and save the file. And it's gonna be a big file anyway, but we'll deal with that. So we're gonna call this stage2.exe. Actually, sorry, .bin, and I'm gonna save it to the desktop. Okay, and then I'm going to go and copy off that stuff that was saved at 9. Go to that address. Nope, it's 9 4/0. Okay, what's going on here? Copy that. I'd like to go to this address, please. Frustrating. Okay, so the reason why that's being angry with me right now is I'm gonna put a label here, is I was in the wrong segment, so it's not able to jump properly. Sorry, I should explain this better. So the reason why I wasn't able to do that is because I was using the address of the memory address of the remote process stupidly. So it's actually the address that I want is this one right here. And so that should work for me now. And I'm just gonna jump over here, open this in a hex file, and go to this address. Why did I copy the wrong one? This is very frustrating. Okay, all right, this should work for me. Okay, so here's all that data. We can see it's just a data blob here, but I'm gonna copy it out anyway. I come down here to oops. Okay. It's just too quick with the mouse here. I'm gonna do this a little bit slower. So I'm gonna come down and I'm gonna just grab everything out of this buffer as well, or out of this memory segment. Be a little bit faster here. Ooh. Is that the end of it? I think that might be the end of it, but I'll just grab a bunch more just in case. And again, I could have saved myself the hassle of this if I'd actually just checked the length of the section buffer. Just kind of dumb of me to not do that. Anyway, so I'm gonna grab this and save it to file, and I'm gonna call this dump _91234 .bin. And I save that to desktop. Okay, so now I'm gonna stop debugging, and I'm gonna pop over to my victim VM, and I'm gonna kill these explorer.exe suspended processes that have started. Not that they're not doing any harm, but I'm just gonna kill them anyway, just to make everything nice and clean. Okay. Okay, so now that we've saved the injected code and then the mystery dump at 940 hex, we're going to have to actually unmap the injected code. And just to explain again, when a binary is loaded to be actually executed in memory, it's transformed from its unmapped version, so the version that's on disk, into a map version, which means that all of the sections are moved into their virtual address, into the virtual addresses that they're listed at in the PE header. So because we copied this file out as it was, because it was injected when it was copied out, it would be in its mapped format. So we need to unmap it. We need to revert it back into its unmapped format so that we can actually work with it like a PE file. So to do this, there's a pretty cool tool from Hashrazade called PEonMapper. There's also a similar one from our site called rebuild.py, which is a Python version, but we don't handle relocation like she does. She has a better relocation algorithm. So I'm just going to show you how to use hers. It works fine, and until we fix ours, you should definitely use hers. So here we are. We'll just go into our desktop here, and it's PEonMapper. And the way it works is you feed it in the mapped code, so the code that we dumped, so stage2.bin, and then you give it the hex address offset where it was actually mapped in memory. Now remember, if we go back to our notes here, we're going to unmap it as if it was run in the injected process. So remember the mapped address in the injected process was this one with a bunch of zeros after it. So we actually need to copy that address over. Don't use the address that it actually existed at in your own process, because it wasn't mapped to be run in your own process. It's mapped to be run in the injected process. So we'll just paste this in here. and we're going to call it stage2.exe, stage2.exe. Okay, success. It's successfully unmapped. And so let's close this out. Ooh, look at that. It's got an explorer.exe icon. This might not be good, actually. Let's open it up in IDA. Let's just give it a new instance here. And new stage2.exe. Open this up, and let's see what we've got. So we'll just give it a minute to, no, I don't want to load the PDB. So this actually doesn't look good at all. So what this is telling us is that this is actually mostly the code from explorer.exe. So like the PDB string is intact and everything. No, I don't want to load that. So let's take a look and see what was injected. Generally, just to make it clear about what I'm talking about here, when you have an injected PE file, the best case scenario is when that PE file is entirely new. So it's actually the payload of the malware has been injected completely into the process. They call it like process hollowing, where you've basically overwritten the entire process with your own PE file. Now that's what I had originally thought was happening here, because we had a PE file that was mapped into the remote process, and it was a full PE file, right? It wasn't just a segment, it was the whole PE file. So I thought, aha, this sounds good. It looks like we have, it looks like we've actually mapped the, the entire PE file in. So we should be able to just dump that out, unmap it, and then it should be the payload of the malware. Now, the reason why I keep on saying, uh-oh, or this doesn't look good, is because this doesn't look like the payload for malware. This looks like explorer.exe, the process that was injected into. So what might have happened is maybe they injected some code into explorer.exe, but they didn't really inject an entire payload in there. So that's what we're going to find out now. So here we have something that looks a lot like explorer.exe. If we look at the imports, these are, well, I mean, you guys probably don't know this, but these are, or you may not. I mean, if you know this, you're, you know a lot more about Windows internals than I do, because, I mean, I know now that these are the imports for explorer.exe, but these definitely look like, this looks kind of like on explorer.exe. If we look at like the strings in here, these are definitely familiar to me. Those are definitely strings from explorer.exe. So let's take a look at the start here and see what was actually injected. Okay, so here, this is interesting. This is definitely not a standard function start, right? So you don't generally, there's no like stack setup or anything. There's just, we just get right into it, right? Let's start moving stuff into registers. That's weird for sure. And then there's a bunch of other crap in here. Oh, hey, look, there's our address. Remember that address 9 and 4 zeros that we dumped a bunch of memory out of? That might be interesting. Here it is again. That 9 and this looks like it's a bit of an offset into it. This could be interesting. It looks like maybe this is some like shellcode that was injected into explorer.exe instead of injecting a full PE file. So even though we were able to extract a full PE file that was injected, it looks like there's only a small amount of it that was changed, the stuff right in the start menu here. So let's take a closer look at this. Now I'm going to actually, if we look here, it's kind of obvious. So it looks like there's a bit of XOR going on here too. Very interesting. So I'm going to cheat a little bit just because it makes it way easier to understand what's going on. So I'm just going to pop over into the decompiler so we can have a better view of what this looks like. It's just going to be a lot easier for me to explain without going through the assembly if you look at what's actually happening here. So it looks like when this binary is run, I don't think it's going to do anything. In fact, I think it's going to crash because there's no setup in start, and immediately it moves a random address. I mean, you can see it's not even within the base So you can see our base is going to be at like that, that 1 and a bunch of zeros is the image base. You can see we're not even in the image base. We're just like way out there somewhere in memory. We're going to move something from somewhere in memory that probably doesn't exist, and then we're going to do some XOR stuff on it. So to me, that sounds a lot like this probably expects some other stuff to already be present in the process in order to run. This doesn't look like the payload to me. This looks a lot like some injected shellcode. So what I'm going to do instead is I'm going to go back and I'm going to take a look in a hex editor at this this offset here. So remember, we dumped a bunch of code that was at address 9 and 4 zeros. So I'm going to look at that code. I'm going to look at offset 5B2 and just see, is there something interesting there? Is this actually a reference to that code? So let me just, I'm actually, in order to do this in a sane way, I'm going to copy that dump here. I'm going to copy it, and I'm going to copy it over to our share folder so that I can open it in a hex editor that doesn't suck. There we go. And I'll pop over to here. Let's open my trusty hex editor. Open this up. Open up the dump. And what was that offset again? Let's see here. Stage 2, please. The offset was 5B2. All right, so let's take a look here at 5B2. Oh. Interesting. Okay, so there's a bunch of junk up here. And then once we get down to 5B2, there's a bunch of zeros. And then 5B2, we see a bunch more junk code. So this looks like it matches up, right? I mean, I don't know. I'm just assuming, like, whenever that shellcode ran, it's going to assume that something was injected at 9 and 4 zeros. And it's going to try and access this offset here. So, this is probably what we're looking at. So what I'm going to do here is I'm actually going to just remove this so that this is at the beginning of the file. And because I don't want to actually run that shellcode, I'm just going to delete this so that the beginning of the file is this interesting offset. And I'm going to save this. I'm going to relabel it here. I'm going to relabel it dump 9. So I'm going to relabel it 9 and 905. What was it? 5B something? 5B4? Let's try that. 5B2, 905B2, B2. Okay, there we go. And I'm going to go back and I'm going to take a look at this algorithm. So we pop over, it looks like we, while V2, so it looks like we copy over this many bytes. C000 bytes from this offset, and we run it through this what looks like a decryption algorithm. So I'm going to replicate this decryption algorithm in Python, and I'm going to take that dump file, the 9.5b2 dump file, and I'm going to run it through that decryption algorithm and see what it spits out. Now, through the magic of video, I'm going to just quickly do this off screen because watching me write Python is boring. Okay, that was easy. Now let's go check out our newly created Python script that has just recreated this algorithm. So let's take a look at it, decode.py. So all we're doing, we just basically took the same algorithm. So you can see here, it's just a rotate left with an XOR in it. And the key, if we go back and show you here, the key was this V1 here. You can see it's actually being used in the XOR, rotate, add 1. You can see here, no magic. Here's your key. You're doing the XOR, rotate, add 1. So same difference. I've just created it in Python. So let's use that Python script and we'll do it live. So with open as read binary as fp, and we'll call it data equals fp dot read. Okay, so I've read in that dump 9 and 4 zeros at the offset 5b2, right? That's what I've just read in here. So now that's sitting in our data, and now we're just going to import that decode script, and then we're going to do a decode. Actually, I can't remember what I called it. Unpacked our data. All right, so decode dot unpack underscore our data of data, and let's save that to something called like PE file equals. All right, and let's take a look at it to make sure it actually was a PE file. Now, you guys know I've done this before, so I can tell you it is, but we'll just double verify PE file. Let's just print out like the first 100 bytes, I guess. Oops, give me 100 bytes. Okay, there you go. So there's your MZ header. You start to do that like the DOS string here. So we know that basically if we go back here, what we've done is we've confirmed that this little injected shellcode expects the mapped section at 9 and 4 zeros. It reads in that code, then deobfuscates it inside the injected process, and then it must map it somewhere and run it. That part, again, we could like follow through how it does it. It looks like it copies it over into some memory, but we don't really care, right? Because we have the PE file now, which we decoded by ourselves with Python. So we can now use that. So let's just check to make sure that that is the final stage. So I'm gonna just go and write out that PE file that we decoded to something called like final stage.exe. So with open final.exe, and we're going to write some binary here. fp fp.write PE file. Okay, so let's pop back over into. So finally, what we want to do is we want to check whether that the binary that we just extracted, we want to check whether it was mapped or not. So I remember saying like maybe they've like mapped it over somewhere else, but perhaps it's actually already mapped. And if I look here, I can see it looks like they're actually directly referencing something in that like 9000 or 940x hex address directly. So perhaps it's already mapped. So let's just do a quick check here and see if we can unmap it. So, and then we'll open it in IDA and see if it worked. So remember, again, we talked about this all throughout the tutorial. There's two versions or two like states that a PE file can be in. It can be like unmapped, which is what it's like on disk, so just the file itself, or map, which means expanded in virtual memory and ready to actually execute as a process. So because I think they were jumping directly to it, it probably was, we'll just copy final.exe over. It probably was mapped. So I'm just going to use HashRezade's cool tool here and see PEonMapper and see if we can unmap it. And then we have both versions. So we have final.exe and then we'll have an unmapped final.exe, and we'll just open them both in IDA and see which one is legit. So, cd into desktop, and then we want the PEonMapper, and it's going to be final.exe. And as for the address that it was mapped at, I think, I don't think I know. I know that it was mapped at that offset because that's where the MZ header started. So it's this offset right here, which is where the MZ header actually started. So we're going to use that as the address, and the output is going to be final underscore unmapped.exe. Okay, it actually worked. So this means it probably was mapped. So let's let's take a look at final unmapped in IDA and see whether that's a valid PE and whether it's the payload. So let's open a new instance, final unmapped.exe. Okay, load it up. Okay, no complaints, no errors. Oh, it's a DLL. Obviously, it's a DLL. So we have a DLL, export, imports. All the imports are good. Let's check out the strings. Hey, okay, that looks like some malware. So we've got ourselves a user agent string here. So I think that we are base config, interesting. So I think that we finally have our payload, our final stage here. And since it is a DLL, so I'm just gonna close this out and I will rename this .dll. Yes, please change it. And so there's our final .dll. So that that concludes the tutorial here today. So that's how you would basically go manually from what we had, which wasn't even running in a sandbox, to the final extracted payload. Now, I do want to mention something here. So this was like a lot of work, a lot of manual work, especially the having to write that small like decryptor in Python. It's kind of a pain, and this is really not a standard injection. Generally, like I was saying before, the packers will just inject the full PE. This is a little bit more tricky. Now, the key here though is that with this injected DLL, you might actually be able to just use volatility and malfind to dump the DLL out of the explorer.exe process space. So I won't show that here in this tutorial because this was about how to manually unpack stuff. So you know with 100% precision, like this is actually the payload. But I do just want to note here that I think because the process space would have been read-write executable and it's probably not part of the explorer.exe PE mapped sections, I do believe that malfind from volatility will actually grab this. So you could have saved yourself all that time and just used malfind and volatility and just dumped out the process. But this is how you do it manually. I hope this was interesting. I hope you learned something. Please do give me some feedback. Let me know if there's stuff that you want me to skip over. I know that I'm trying to explain stuff in detail, so it can get a little bit tedious, a little bit boring. Hopefully it's not too boring. So yeah, feedback is great. Let me know what you want to see more of, less of. And remember, keep exposing the mechanics behind the malware and stay curious.